Among the areas that CFE Media does a lot of time researching is energy management. Our research manager, Amanda McLemon's here in the room, and works on helping us understand from our reader standpoint the importance of energy management and how it's being deployed. And we're going to talk about that during this session. Eric Scott's an advanced technology specialist for Molex, which has long been involved in industrial communications. Eric's got more than 18 years of experience in product design and development of industrial network systems. As part of this work, he's been participating in the ODVA special interest groups and as part of the ODVA Technical Review Board. He also leads the Molex Canada Profinet Interface Competence Center. This is a vital topic to manufacturers and one that is gaining in prominence, and we're very pleased to welcome from Molex Eric Scott. Eric, good morning.
Good morning. Thank you very much. I hope everybody's enjoying the nice rainy weather, because that was a nice drive in this morning. That's all to say. All right, so let's get started. So what I'll try to talk about today is the cost of energy, and kind of and a little bit of the impact that it has on our factories. The role of industrial networks, that's a primary focus for me in what I'm doing in the ODVA and with any of the Profinet area. Energy usage and reporting standardization. Let's try to get some energy measurements that come back in one format. Today it's coming from everywhere and all different things, right? So, and controlling the usage, and maybe what we can do in connection to the smart grid in the future, and then I'll go through a little bit of the SIP energy itself, mostly because I'm a lot more involved in that, but it's more of an overview of what we can do with energy management, and a small sort of application that I made up to prove some points. So I know a lot of people, it's kind of interesting where your energy comes from. When I was doing the research for this, I didn't realize that 32%, or about 1/3 of our usage of all our energy around the world, is to do with the industrial market. And the other surprising part is residential is 21%. Man, we use a lot of power at home, but. So also in researching this, and I've seen a little bit in some other Profinet seminars, there's studies that suggest that we could save about 15 to 30% of our energy if we just did something with some of the data we had, or do something in our factories. So one of the Profibus International did a study, and they did it at, I think it was a Volkswagen plant. They measured the amount of energy that was being used in the plant from like a regular shift. And then from all that data, they came back and said that they could save like 60% of the energy usage during downtime. And this next, there it goes. So if we look at the nice orange part, lose the arrow, there it is. This nice line here, that's when, on the weekend, when nothing's running. There's not producing anything. This is like an automotive plant producing maybe a Jetta or something, and we got this huge amount of energy, about 60% of what you would normally use. Then they decided, okay, let's turn it off. Let's turn off as much as we possibly can. And then the difference between the two is about that 15 to 30%. So I guarantee they might have had some guesses, but they probably didn't realize it was 60% of their energy that they were using during the weekend just sitting there. So that's kind of the main thing. And another part that I threw in here just to give an idea of how much it is, and I'm sure a lot of you guys know a lot about this part. It seems that right now only about 28% of the motors used are high efficiency motors. And then by 2017, this should be about 62%. And the other part that I thought that was quite interesting is 96% of the cost of your ownership of the motor is actually the energy that it uses. Thought that was, just to give you an idea, motors are going to be one of your biggest uses of energy in, well, in the industrial automation anyway. Process will probably be a different story. So, aspects of energy management, monitoring the energy usage, so figuring out how much we're actually using. Because today, most factories, I guarantee they probably don't know what they're actually using. They may have had some idea when they put the machines in, because they had to figure out, okay, I need this much power for this area of the factory, but they probably don't know how much they're actually using. So let's measure it and figure it out. Then let's control how much energy a machine can use at any given time, and maybe power down the machine while it's not active. And that was the big thing back a few slides on that graph, was actually powering it down. There's a fair number of the industrial protocols that do have support for energy management at the moment. And Profinet, they have a profile for energy monitoring and control. Ethernet IP, and I say Ethernet IP, but that also includes DeviceNet and any of the other SIP networks. And Circos. Circos 3 has energy management and power control. Now, there should be more out there. I'm hoping that some of the other networks come on board with that, but these are the ones that popped up right away. So, energy is not just electrical energy, so we kind of want to try to report things in a common way. One of them would be to report it in kilowatt hours. It's familiar to everybody what that means. And so then we can report energy usage as in how much steam you're using, chilled water, natural gas, oil, all those different types of energies that you're using in your plant, and report it all back up to one system in one format, so being kilowatt hours. Once you do that though, once you're reporting all that information, you can kind of figure out how much you actually cost you to build something, including the energy. So if I build a car now, with those guys that were doing the thing at I believe it was the Volkswagen plant, I can figure how much energy I was actually using to build that one car, because now I know that car went through the line, it cost this much to do that. So there's really two types of approaches for this. There's powering down the machines when they're not used. That was the first example. The next one is that we could power down the machines to a lower level during production. So we can produce less, but keep our demand for energy at a lower rate for maybe during the middle of the day when the air conditioners are all on everywhere and we need to save a little bit of power because we don't want to get charged that extra amount of money from the utilities because we went over the peak demand for that day. So you may not save energy as a total, but your total cost could come down. So one of the times that you could power down your machines would be lunch, weekends, maybe if you have a scheduled break, maybe some maintenance on a machine, even unscheduled. The machine goes down because something breaks. Why do I let the rest of the line sit there and run if I know I'm going to be down for 3 hours? Because I got to fix this thing. So shut it down. I'm not going to spend that much energy. There's no point in letting it sit there. And maybe that line is idle because we've produced we had a stoppage on another line. So now your machines are idle. Why are we running the power? Now there's things to consider there because how much time does it take to start the thing back up? if we have a heater, a glue gun or something, you've got the pot of glue, if you let it cool down, it's going to take so much energy to get it back up to temperature again. How long does that take? Or even if it takes, say it takes 10 minutes to warm back up, because if I want to shut it down for 15 minutes, am I actually saving any energy there? So there's things to consider. It may actually take more energy to get it back up to temperature than holding it there. Now maybe glue is not a good example for that, but there's a few things that can run into that area. Running at a lower power level during production. Now this is tricky. It's where I'm doing a lot of work in the ODVA at the moment and trying to figure out the use cases for this. This is interesting because the reason you would do it is mostly for demand response type thing. So the utilities come along and tell you, you can only go up to so many kilowatt hours. Let's bring the energy usage down for that time period, or you don't want to go over it because you have a quota for the month. And this is why I say due to overage penalty charges. External environment factors. So we have a storm somewhere, power lines go down. You may get asked to bring the power down so you don't blow the rest of the transformers in the area. But you still don't want to stop producing something, because that's how you make your money. But you may want to bring the power level down to work at that. It may be you're an energy conscious type, you're promoting that type factory, and you're promoting that in your place. So you want to say, I don't want to build something if the coal power generation plant's online instead of using hydro or wind. I know that for somehow, in the future, because all the smart grid's getting a little bit better at that, I know that I'm not using solar or wind for that, but I'm using coal. So let's maybe not produce so much now, then we can tell people our percentage of coal in our energy usage is lower. So there's different reasons, and that's one of them. So this is what, right now there's a lot of protocol, a lot of the major protocols are working on how to control and manage the energy, but the connection to the smart grid will be the next step. How do we do that, and why do we do it? One of the things that I believe we need to do is it needs to be some kind of translation, because I'm pretty sure you guys that are running factories are going to say, I don't want the utilities coming in to tell me to turn off something like they do with our air conditioners in our houses if we want. You can sign up for some program, at least where I'm in Canada, you can say, I want to sign up and they'll turn my air down in my house during the middle of the day because I want to save some power. I'm pretty sure factories don't want them to come and do that. So you're going to want some kind of translation between that. You get the command from the smart grid or from the standards that are involved in that, like 61850. And then once you get that command, you can decide, okay, does this make sense for me to do this now? Or do I want to pay the overage charge because I need to produce this today? But the smart grid part is not quite there yet, but it is something that needs to be thought through coming up. Now, I know there's questions at the end, but I'm going to jump into a little bit more technical section for a second. So if there's some short questions now for all this part in the front, it may be a good time.
What do you see the timeline of the smart grid doing some of the things that we think it will? You know, we're talking 20. Do you have an idea of
So,
get everything out of that that we want?
so the question is what the timeline may be for smart grid to get involved. Honest answer, I don't know, because it's standards. They just take a long time for these to get moving, right? I've been working on the SIP energy part for the past 3 or 4 years, I think. And so now the protocol parts are there, and then the 61850 stuff, that's coming along just fine. but I don't see it in the next, I would say at least 3 years or 4 years, right? So maybe 2020 isn't that far off. It's just, it will be a little bit, because I think people will also be scared. The other thing that I've noticed in talking to customers, because we do stacks and stuff for networks, right? So I talked to some of the customers and they're like, the guys on the factory floor say, we don't want to do that because when I shut something down, it may not come back up. And every time I do that, there's a problem with it. So I'm a little bit worried about it. Their management saying we need to save energy. So there's still a struggle, even in the factories, to try to figure out what the best approach is. It's probably going to be the same sort of thing as IT and the industrial network guys arguing for a while. They're finally understanding each other now, but I think that's going to happen the same way with energy for a while. That's my impression from what I hear from the different companies that sit on the SIGs that I'm in. Okay. So because I'm involved in the ODV a fair bit, I'll go through very high level what SIP energy looks like. This slide's just to give you an idea of sort of the architecture of how SIP works. SIP is more object-based. So what they did when when we added SIP energy, we just added a whole bunch more objects. Objects that control energy curtailment. So this is the production level type thing. Power management, this is turning it off while you're not running, idle state. And then collecting data. So I can collect data into a common piece, which is the base energy object, and non-electrical, so that's where all the steam, steam, oil, and all this stuff shows up, and then electrical energy specifics. So the concept that at least SIP energy did was to split it up into electrical and non-electrical energy, and then bring that up into a common place. So then that's where this base object comes from. And there's always an association between the two. So if you want to know how much oil you're using, then you go to the non-electrical one and the data's there. But if you go to the base one, you know what it is in the same kilowatt hours that you would have if you were looking at steam, or if you were looking at electrical energy for your plant. So it normalizes, the base energy object, as I said, it normalizes all the energy into kilowatt hours or kilowatts, so your power that's instantaneous power. And it can be a big number, because these are like odometers in your car. They just keep rolling and rolling and rolling until you get to the 1 million mark in your car. This ends up going to 999 terawatts. Seems like a lot, and you'll probably never get there for a long time, but it's just a couple extra bytes. The electrical energy object gives you things like knowing what your reactive power is for your total, your line, per line, active power, phase, line frequency, a whole bunch of variables that I'm looking at being a protocol guy going, that's a lot more information I know, but I can figure out how to get it to people easily. And that's the point here with the networks, is getting the information to people that know what it is in a common theme. So the non-electrical object gives you a way to report energy, all kinds of energy, even this strange thing called tau. If anybody knows what tau is, maybe you can explain it to me. One of the guys that's on the energy SIG keeps telling me this tau, just because it sounds good, I think. Anyway, so then it gets translated into kilowatt hours in the base energy object. And then there's math within that non-electrical objects to allow you to translate pretty much whatever you want. So if you have some other energy that you want to translate to kilowatt hours, there you go. So there's a couple different ways that we can look at measurement of the energy, or how we can bring that data in. One of them being actual measured, so you're actually measuring the values of the kilowatt hours that the motor is doing, or you derive it. So I got the voltage, I got the current, but I don't know a few other variables, so I just guess. So you get some kind of percentage accuracy based on that, and the object will give you that information so you know what your base is. The other thing that we provided in this is that you can proxy something. So if you have an old system that you want to bring into the network, you can proxy it and just make it look like it's coming into SIP energy, that is. The other important part on this is the energy aggregation, the aggregator. So I can take and I can make this energy object look at a whole bunch of other energy objects in your plant, so then it can go to cell 1, cell 2, cell 3, cell 4, and it all brings it into one. There's your line. But within that cell, I can also say within the cell I got motor 1, 2, robot controller 1, robot controller 2, and they'll all come back up in an aggregation format. So that's all put into into these objects. So the power management object was the one that allows us to lower the power state when it's non-operational. I bring this to something like your laptop. You can bring your laptop to hibernate, which saves all the data to your hard drive, and then you shut it down. But when I do that, when I open the lid back up, it takes a couple minutes for it to start back up. But if I put it into sleep, it stores it into RAM, which takes more more energy. But then when I lift the lid, it opens up right away. So I'm still saving energy, but it's the amount of time it takes for me to actually to deal with the startup again. So there's a couple different ways of looking at it. And so and when we were doing the object, that's what we did. So energy management, at least in the SIP world and Profinet, they both do it the same sort of way, and I believe Circos does it the same. So we request, oops, wrong button. We request where we go? We request the time to go to sleep or pause, and then there is a certain amount of time it takes to get to that power level. So coming down to the hibernate or the sleep mode in your laptop, then it takes time to wake up to the point where you can actually tell it something on the network. Tell it to go back to a runtime, and that's this resume time. So then there is a certain amount of time that is actually the minimum. If I'm going to use my laptop here and type one sentence and go, okay, now I'm going to close the lid and start and lift it back up, that's probably not going to save me anything because I'm doing more. Bad example, but that's okay. I think. And power curtailment. So power curtailment is more of the runtime area. So there's an object, power curtailment object. It's dealing with the fact that maybe I want to go and tell my machine that I want to run at 70%. So I give it a command. I want you to run at 70% now because I've looked at the overall factory. I need to bring my power down for the middle of the day, for instance. So I'm going to tell everybody go to 70%. So I can do that. I could also come back and tell it to go to 50, 30, and you can set all these things up. One of the concepts for this is that I have a cell. I kind of teach it. I run it at full speed. That's your 100%. I teach it that, okay, if I tell you to go to 70%, this is all your parameters. I'm going to save it and run from there. I teach it to go to 50%. I save it, and I can run it from there. And I can go along. Somebody asks me to go to 50. I just go to 50, save all those parameters, come back up. Later on, I can go back up to 70 based on what the power is going. So that's the idea of these objects and how they can be used. But they're all common. This is something that every vendor that's using SIP would have the same interface. It wouldn't be different. And today, any energy management stuff that any of the guys that are on the SIG with me, they say, it's all different. Everybody does their own thing, so there's nothing common about it. So then this will help everybody to implement it much better. So I got a little example, and I'm a protocol guy, right? So look at the cell. It doesn't mean anything. I just needed some robots because I could get some numbers from there. So I have a couple robot controllers. I put a glue gun in there, drive controller, some I/O blocks, and then if we go to this, so our energy management tool, the client side, is sitting up here, and it's telling me that this factory, maybe, it's got 15 kilowatts of energy. But that's all coming down from, I got a line PLC that's aggregating all the data from the one part of the system that's dealing with, and then I got another one. So this section here was this line. Oop, there we go. The projector's too far away. Anyway, so it's that side. And if I go back, so that line PLC is at, the angle's too much, I can't even see my numbers from there, 7 kilowatts. But if I go to the drive controller, saying it's doing 100, maybe my numbers are a little off, but the idea is, and in the robot controller, these numbers are not too far off. So the robot controller has two things. It's robot arm, he's moving something, but he's doing something at the end of the robot. So I put two instances in here. So I can figure out what the robot's actually doing at the end of the arm for how much energy it's using, how much the robot's doing it, and add those two together. It goes back up to the line PLC as the integration. And then the second robot controller, same sort of thing, but the end of the arm or the I/O blocks that are attached to it, not at the end of the arm, the I/O blocks that are attached to it, I threw a proxy in here to give you an idea that it's not always just a drive that you need to get the energy from, or not always something really smart. I could have an I/O block that says, I turn that thing on, all of a sudden I'm going to be using 0.5 or 5 kilowatts. Okay, so every time it's on, I'm using 5 kilowatts. I can still report that up to the energy management system. So what can we do? Helps us understand how much energy is being consumed, so we can decide what to do at the cell level. Instead of getting your big utility meter at the front of your factory saying, yeah, I used that much energy today. I don't know where. Now I know it was that cell was producing a lot more than this one or that one. You can compare the energy usage that you had from a month ago to this month to the next month and go, oh, there's something weird here because I keep using more and more and more and more, but maybe the bearings are going, maybe something's going, so even give you some help with some preventative maintenance. You can schedule jobs in your plant floor to try to keep your peak energy usage down so you don't go over those nice peaks and pay for energy that you're not really using. And then you can use the energy that you're collecting to set up curtailment things so you can deal with the demand response. And that went a little bit faster than I expected, so there's lots of time for questions.
What are some of the practical differences in looking how energy is managed among the three protocols? And how does that affect end users or equipment manufacturers or system integrators when they're dealing with this?
So that's a tricky question because being from a place that I will deal with Profinet, Ethernet IP, pretty much any of the industrial networks, I think a lot of it's going to be down. You're going to be using the protocol that either maybe you're in the Rockwell camp or you're in the Siemens camp. So you're probably, first of all, you're probably going to be using those. But there are some differences in at least the two first ones. Circos, I think it's pretty close to SIP. Actually, maybe actually closer more to Profinet. But one of the big difference for the SIP one is the aggregation part is built in. So I can start collecting that data from level to level to level. Profinet inherently does not have that level of aggregation built into it. They both have sort of when you're powering something down, it's time-based. So I go and ask, how long do you want me to power down? And they all have levels to do it. Now, the way they do it is slightly different, but the concepts are the same. That's why when I put this together, I thought, okay, I'll stick to the ODVA stuff because I'm a little bit more familiar with it, but the concepts are the same. The running at production part, that's pretty new in the ODVA side, and I'm not sure that it exists anywhere else at the moment. Does that answer your question?
Eric, got a question back. Got a question back here.
Energy seems to be a very important thing to monitor these days for a couple of reasons. I know that there's an initiative in the state of California and several other states where energy is becoming more of a variable cost.
Yeah.
Because they can call you with a 20-minute window and say, we're going to charge you 8 times the value of your current price of energy. They can do that because they're giving you a deal and they're actually trying to get you to phase back.
Right.
Is that becoming more of is that going to become more of the trend everywhere, or is that simply exceptions in certain states?
I'm hearing more of that, but I'm dealing more with the protocol, so I'm not sure. I'm hearing that because of all the different companies that I sit with. So I believe so. I think you are going to see that more. But that's coming from sort of the third person, so I don't want to give you sort of the government answer or the state answer on that.
Like I said, I'm just looking for, I mean, you're focused on that field, so I'm looking for what is the trend? Is this going to go nationwide over
I think that's where the demand
next
response.
10 years or 25 years, or what are you
That's
saying?
why we have to look at the demand response part, and that's why we've been focusing on it for the last little bit. So the large companies on the ODVA side, being Schneider and Rockwell, are definitely focusing on those things. So I do see that.
So then what I'm hearing is, if we're not monitoring the energy now,
You're going to have a hard
We
time
will be.
figuring out, yeah.
in order to be able to meet the demands of what the energy producers are actually foisting upon all of us.
Yep.
And one of the things we've talked about in both plant engineering and control engineering over the last several years is the idea of energy as a managed cost rather than a utility bill. And that's been probably the biggest change we've seen in this area over the last 3 or 4 years, is this is now a cost that you measure rather than a bill that you pay.
So one of the things that I said in the middle of the slides was that you may want to bring your energy usage during the middle of the day down. That doesn't mean that you're using less energy. It just means your bill is going to be less because you didn't go over that peak that they told you that you need to come down to. So you may actually have to use more energy over a longer period of time, but so be it. It's cost you less.
We've seen the rise in VFDs and some of the other areas in energy management at the device level and now also at the automation level. But the energy companies, the utilities, are looking at this from the standpoint of saying it's cheaper for us to manage the energy that we've got now rather than to build new capacity. It also takes less time and less capital expenditures. So they're trying to squeeze the accordion as tightly as they possibly can while giving a reasonable break to to the manufacturers who are looking to use this.
So the smart grid integration may come a lot sooner than what people want to happen is what I'm getting out of that, but yeah.
Got a question over here?
Thank you. Hello, Eric. We're seeing a lot of standards and regulations written around the component base, example of motors, the high efficiency motors. In the future, do we see this being more holistic now that we have the capability of measuring a lot more of our system parameters from the regulations and standpoint, or do we see this more being just mitigated by the power companies?
There are standards that I know in Germany, there's a fair number of standards that are coming out to say you will limit your power that you're using or do put high efficiency motors in or whatever, right? Now, being the protocol guy, that's not really my realm. That's what I hear in the SIGs.
I'm just wondering, future, is it going to move to cell-based where it'll be robotic cells are going to have a certain amount of efficiency standards that they have to meet, machine-based, plant-based? Now that we have this capability to measure, or do we think it's just really going to be more regulated by the power companies?
That I don't know, but I do think there's going to be a fair number of regulations put in place, and some of them are already there. They're just saying, okay, it'll be this year coming. But I'm not in that world. I'm more of the protocol side. So
I know that the research that plant engineering and control engineering has done about energy management say that more people in the plant are given incentives based on their energy use. So it may be a self-controlling thing that people are looking to reduce energy cost as a cost of manufacturing production.
Yeah, and I'd add to that regulation, particularly in the U.S., is a really dirty word. So we're trying to avoid that as much as possible, but we still face the issue of the utilities having finite capacity and an expanding base. So they're looking to trying to get around regulation by having it be more of a shared responsibility with the manufacturers and with their other end users as well. You're starting to see, even in the residential area, which I know Mark's involved in as well, in some of the residential homes, they're looking at how can we monitor and manage energy on a continuing basis through smart devices, through other things. And a lot of the manufacturers we go into are looking at things like how do you motion sensors for lights, just individual, small incremental things, the low-hanging fruit. Other questions? Because this is going to be an expensive topic over the next 3 or 5 years, and then beyond as we continue to go at that. With nothing else, I want to thank Eric for the presentation today. We've got some networking time. Lunch is going to be served about 11:45, and then we invite you to stick around for our afternoon keynote and the afternoon presentations. But this will be a great time to get a chance to meet some of the CFE editors and folks here on staff. We've all got our badges, but we'd like to get as much feedback from you in terms of other topics that you're looking for us to be covering in control engineering and plant engineering in the coming years, and it's a great opportunity for us to do some networking with you as well. So thank you very much, and we'll see you at lunch.